Not all graphs are the same. Some are mirrored, some are rotated, some have not particular pattern. Let's see what the story is about. I'm Saba and this is Hidden Math.
In this video, we're going to learn how to tell if a function is even or odd. I'll show you both a quick and easy way and the standard method used in math books. So let's get started. The first thing is to check whether a function is even or not. A function is even if and only if f of negative x equals f of x. That is, if you replace x with negative x and nothing changes, and the new function is exactly the same as the original function, then the function is called an even function. Now, what about an odd function? It is very simple. A function is odd if f of negative x equals negative f of x. That is, if you replace x with negative x, then all the terms of the function change sign. And if even one term does not change sign, then the function is no longer considered an odd function. Now, what is the last category? A function that is neither even nor odd. A function is neither even nor odd if, when you replace x with negative x, some terms change sign and some remain unchanged. In that case, the function satisfies neither the condition of being even nor the condition of being odd. In mathematical terms, f of negative x is neither equal to negative f of x nor equal to f of x. So we have defined them so far. But until you solve the problem and see an example of it, you still cannot say whether you fully understand it or not. Let's start with this example. Suppose if x is equal to x to the power of 4 plus 3, x to the power of 2. What do you think this function is? Even, odd, or neither? The easy and quick way is to look at the powers. That is, see if the power of each term is even or odd. The power of 4 is even. The power of 2 is even. So I can easily say that this function is an even function. So if all the powers are even, it is an even function. To prove it formally, you have to replace x with negative x. So we get negative x to the power of 4 plus 3 times negative x to the power of 2. Negative x to the power of 4 means multiplying negative x by itself 4 times, which gives a positive result. Negative x to the power of 2 means multiplying negative x by itself twice, which also gives a positive result. In general, whenever the number of negative signs is even, the result of their multiplication is always positive. So in the case of this function, it becomes odd x to the power of 4 plus 3, x to the power of 2. So we conclude that f of negative x equals f of x, and this function is an even function. Let's look at another example. Suppose if x is equal to x to the power of 5 plus x to the power of 3. So the coefficients in front of the variables do not matter. It is the exponent of the variable that matters. Because the exponent of all the terms of this function is odd, we say that this function is an odd function. Now let's prove it. Instead of x, we put negative x. Remember that whenever the number of negative factors multiplied together is odd, the result is always negative. So, negative x to the power of 5 is equal to negative x to the power of 5. Look, you have to pay attention to parentheses in mathematics. They play an important role. And negative x to the power of 3 means negative x multiplied by negative x multiplied by negative x, which gives a negative result. So here we can write the expression like this. Negative x to the power of 5 minus x to the power of 3. Now if we factor out negative 1, we get negative 1 times open parentheses, x to the power of 5 plus x to the power of 3, close parentheses. What is inside the parentheses is exactly the original function. So we conclude that f of negative x equals negative f of x. So this function is an odd function. Now let's examine another example. Suppose f of x is equal to x to the power of 2 plus 1. We know that x to the power of 2 has an even exponent. But what about the constant term? You can also write it as 1 times x to the power of 0. Anything to the power of 0 is equal to 1, and since 0 is considered an even number, all the powers in this function are even. So we can say that this is an even function, even without substituting negative x. But if we are asked to prove it, we replace x with negative x. Negative x to the power of 2 plus 1, which simplifies 2x to the power of 2 plus 1. So we conclude that f of negative x equals f of x. Therefore, this function is an even function. Well, we see that the function has not changed. Sof of negative x equals f of x. And we conclude that this function is even. Here we can make an important conclusion. If you see a constant number, consider it even, and think of it as that number multiplied by x to the power of 0. And 0 is an even number, just like 2, 4, and 6. Another example is f of x is equal to x to the power of 3 minus 8x. Is it even or odd? X to the power of 3 is odd, and x to the power of 1 is also odd. So this function is considered an odd function. I would like to remind you again that the coefficient of the variable has no effect on whether the term is even or odd. Let's quickly prove it. Instead of x, we put negative x to the power of 3 minus 8 times. Negative x, it becomes negative x to the power of 3 plus 8x. So here, f of negative x becomes negative f of x, and we have proved that this function is an odd function. And that's it. Now let's look at another example. Suppose f of x is equal to x to the power of 3 minus 5x to the power of 2 plus 2. So our first term has power 3, which is odd. Our second term has power 2, which is even. Whenever you see even and odd powers together, you understand that the function is neither. That is, it is neither even nor odd. This is how to identify a function that is neither odd nor even. Now let's prove it. To prove this, wherever we see x, we replace it with negative x. Negative x to the power of 3 minus 5 times. Negative x to the power of 2 plus 2. This becomes negative x to the power of 3 minus 5, x to the power of 2 plus 2. This function f of negative x is not equal to negative f of x, and it is not equal to f of x. So as a result, this function is neither even nor odd. Now in this section, let's talk about the graph. How can we tell, just by looking at a graph, whether a function is even, odd, or neither? An even function is symmetric about the y-axis. What does that mean? It means that if you fold the graph of an even function along the y-axis, the right side will fall exactly on the left side. For example, look at this function. F of x is equal to x to the power of 2. Since it is even, we know that the function is an even function. The graph looks like a U shape. If you fold it along the y-axis, the left and right sides fall exactly on top of each other. So the function is even. Now look at this function. F of x is equal to 3. Yes, this is a constant function. We know that this function is an even function. In fact, you can think of it as 3 times x to the power of 0. And since 0 is even, we consider this an even function. The graph looks like a horizontal line. Don't say that the left and right sides do not match. Look, this line continues from negative infinity to positive infinity. So no matter how far you extend it, both sides remain perfectly symmetric. So here we conclude that constant functions, like f of x equals 3, have even symmetry. What is the graph of an odd function? How can we recognize it? An odd function is symmetric about the origin. Let me explain it in a simpler way. If you rotate the graph 180 degrees around the origin, it falls exactly on itself. That means the first and third quadrants are mirror images of each other, and the second and fourth quadrants are also symmetric with respect to the origin. For example, the function f of x is equal to x to the power of 3 is an odd function. Its graph is increasing, and you can see that the first quadrant is like a mirror image of the third quadrant. If you rotate it 180 degrees around the origin, it falls exactly on itself. Now look at another simple odd function. F of x is equal to x. This is a straight line passing through the origin at a 45-degree angle. You can see that the first and third quadrants are symmetric, so this is also an odd function. So the graph of an odd function has symmetry about the origin. Now, if a function is neither, that is, neither even nor odd, then what do we know? It means the function is neither symmetric about the y-axis nor symmetric about the origin. For example, look at this graph. Do you think this function is even, odd, or neither? It is not symmetric about the axis and not symmetric about the origin, so it is neither. This graph is similar to the function f of x is equal to x plus x squared. And according to the definitions, when we have both an even power and an odd power, the function is neither. So knowing the graphs is very important because sometimes they do not give you the formula and they just want you to determine from the graph whether the function is even, odd, or neither. For example, look at this one. It looks a little like the function f of x is equal to x to the power of 2. But if you look closely, it is not symmetric about the y-axis and not symmetric about the origin. So it is neither even nor odd. Now consider this function. F of x is equal to x to the power of 3 minus x. How does its graph look? It is not symmetric about the y-axis, because if you fold it over the y-axis, the two sides do not match. But if you look carefully, it is symmetric about the origin. Why? Because the first quadrant matches the third quadrant and the second quadrant matches the fourth quadrant. That means everything you see in the first quadrant appears in the third, and everything in the second appears in the fourth. That is enough to conclude that the function is an odd function. This shape corresponds to the function f of x is equal to x to the power of 3 minus x. Now tell me, is this graph even, odd, or neither? Look, this function is known as the W-shaped function. This graph is symmetric about the y-axis. This is the graph of the function f of x is equal to x to the power of 4 minus a constant. But now, if we make a small change in the formula, for example, if we add on 10th x, you will see that the shape changes like this. It loses its symmetry about the y-axis. It is not symmetric about the origin either, so the answer is neither. This is because we now have both even and odd powers in the function. Now, what if we want to check something that is not a standard function? For example, look at this circle. The general equation of a circle is x squared plus y squared equals r squared. Do you think this is even, odd, or neither? Well, it is symmetric about the y-axis, so it seems even. But wait, the first and third quadrants are also symmetric, and the second and fourth quadrants are also symmetric. So is it both even and odd? The answer is that mathematically, we cannot classify it as even or odd because it is not a function at all. It does not pass the vertical line test. So it is better to say that it belongs to the category of neither, because it is not a function. So in short, being even or odd is a property of functions. If a shape is not a function, we can talk about its symmetry, but we cannot say whether it is even or odd.
Alright, that's it for this video. If you enjoyed, don't forget to like and subscribe. I'll see you in the next video.